Okay, so who is ready for notes?
We are.
Okay. Caitlin, Steven, and Braylon are.
I'm ready. 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 I'm ready.
Go SpongeBob!
A median is a segment that connects the vertex with the midpoint of the opposite side. So you can just do your best job of eyeballing where it looks like the midpoint of a side is, and then drawing a straight line from that point to the opposite vertex. That is a median. So if you repeat that process, if you just kind of eyeball where it looks like the middle of this side is, and then connect that point with the opposite vertex. And then for the last one, finding the midpoint and connecting that with the opposite vertex. You should find something very similar happens where the three medians all meet, as when we did the perpendicular bisectors and the angle bisectors. What do you notice about the location about where all these points, all these lines meet? It's smack dab at one singular point, and that one singular point where all the medians meet is called the centroid. So it's a point of concurrency. The point of concurrency is just where all of the lines intersect, where all of the lines meet. It has a different name depending on what segments are intersecting there. So the centroid is the point of concurrency. Or if you want to say like where they all meet for the medians. And just like how the circumcenter and the incenter had something special about the location of that for those triangles, the centroid has something special about its location based on the triangle that we have here. So for the centroid, the medians of a triangle intersect at a point called the centroid, and it is 2/3 of the distance from each vertex to the midpoint of the opposite side. So it's 2/3 the way across the triangle from vertex to the side. And you can probably tell here, like this is the 2/3 part. This would be the shorter part here. Before we do this next part, let's go ahead and just do a little quick fraction review. If I have a segment, and let's say that segment's 15 units long, if I was going to divide that into thirds, how much would each part be? 5. If you divide it into equal thirds, then each portion would be 5. So what is 2/3 of that? 2/3 would be 10. And then the other part's going to just be 5. So here's the question to make sure you pay attention to. How many times bigger is the 2/3 part than the 1/3 part? 2 times as big. Or the 1/3 part is half as big as the 2/3. Okay, basic fraction stuff there. 2/3 is twice as big as 1/3. But this kind of demonstrates that too. So looking at this question, it says in triangle CED, U is the centroid. So this is the centroid, so that means it's 2/3 the way across. It says UK is 12, EM, so this whole thing is 21, and UD is 9. So just like everything else, this doesn't really have to be drawn to scale, so don't worry about it if it's not. the 2/3 and the 1/3 thing are going to be the important part. So when I'm looking at, like, let's say it started out giving us UK. That's the portion of CK. Is that the 1/3 part or the 2/3 part? That's the 1/3 piece. So how long is CU? It's the 2/3 part, which in this case would be 24. Correct? It's twice as big as the 1/3 part. And then what about CK? How long would CK be? 36. Because if this is 24 and this piece is 12, then the whole thing is 36. Okay, let's look at this piece here. So this is 9, U to D. Is this the 2/3 piece or the 1/3 piece? It's the 2/3 piece. So how could I find the 1/3 piece? Divide it by 2. So sometimes you might get a fraction for this. That's fine. JU would be 4.5 because it's half of the 2/3 part. And then how long is JD if they were to ask me that part? Well, if this is 4.5 and this part's 9, then the whole thing is going to be 13.5. And then for this last part, it says EM, meaning this whole thing is 21. So if the whole thing is 21, I'm not dividing it in half now. Now I need to divide it into equal thirds. So dividing 21 by 3, I have 7. The 1/3 part is 7, and the 2/3 part is going to be 14. So I would know that UE is 14 and UM is 7. So most of what you're going to have to do for this is know that 2/3, 1/3, and depending on what piece they give you, be able to answer questions finding the other parts. Once in a while, they may tell you something else. They may tell you like CJ. Let's say CJ is 10. If CJ is 10, how long is JE? It's 10 because this is the midpoint, and each of those are the same. So just pay attention to like where in the picture these parts are, and then you can answer the questions accordingly. Something else that you need to know about the centroid. The centroid is the center of gravity for a triangle. It would be like the balancing point. So for this one here, it says a performance artist plans on balancing triangular pieces of metal during her next act. One such triangle is placed on a coordinate plane, and these are the vertices. What are the coordinates that the artist should use to support the triangle? So basically, it's this question's asking, where is the centroid? So what I'm going to do is I'm going to take this and just graph these parts. I realized that the way that this copied, it copied pretty light. So if you guys could graph these parts on your own, I think that would kind of speed up the process. If I'm trying to find the centroid, I'm going to be looking for where are those medians. I need to draw in those medians. How would I find the middle of this side beyond just kind of eyeballing it? How could I find the middle of this side? You could use the distance formula and cut it in half, but then you'd still have to go that same distance over. There would be something a little easier that I could use. The midpoint formula. If I just found the midpoint, then I wouldn't have to worry about like adding the distance over. Both of them could work, but this will be, I think, the way you're going to want to use. So if I'm finding the midpoint, let's find the midpoint between these two. Remember, for midpoint, you're averaging. So you're adding the coordinates up and dividing by 2. So in this case, the two x values are 1 and 9. So add those up, you get 10, and divide it by 2, you get 5. The two y values are 10 and 5. So when you add those up, you get 15. Divide that by 2, you get 7.5. So this point here will be at 5, 7.5. Then I can take that point and connect it with the opposite vertex. This is one of the medians. If I repeat that process, let's say I want to find the midpoint of this side. If I repeat that process, I'm adding 9 and 5 and dividing by 2. Oh my goodness. Well, you guys can finish watching this on Monday. See you Monday. So when I add those up and divide by 2, I get 0.5. Yep, so the midpoint of this side is at 7, 2.5. And then you can take those and connect them. So this right here would actually just be the centroid. That's at 5, 1, 2, 3, 4, 5. You could draw that extra centroid in too, but once you get 2 of those, that extra one would just be right there. You could use that as a double check if you wanted to, but that would be the location where all 3 of them meet also.
So I wanted to show you guys how this altitude behaves with each type of triangle. So the altitude is the segment that's perpendicular with this side. And when the triangle's like this, that altitude just kind of slides back and forth. There are a couple scenarios though. If this angle B were to become a right angle, do you notice that the altitude is the same as that side of the triangle? And if I even take this angle and if I make angle B a obtuse angle, that altitude comes outside of the triangle. So you actually have to measure like across here and then go straight down from there. So that's how we're going to start the notes on altitude. I'll first define it. So the altitude is the segment through a vertex that is perpendicular with the opposite side. So when I'm drawing these altitudes in, I want to start at the vertex and I want to go perpendicular with the opposite side. So you can kind of see here, looks like perpendicular is probably right around there. I could even continue to draw these in. I'm going to wait and do that for right now. If you just want to make these altitudes in, for this one here, this altitude would be right there on that side of the triangle. But for this one, I need to go straight down and I need to be perpendicular with that side. So I probably should have like extended this side out first so that you could see that. So this is perpendicular, this is an altitude. This one is an altitude because it's perpendicular with that opposite side. And this one is an altitude because it's perpendicular with that opposite side. Just like for all the other segments we've looked at in this chapter, these segments, these altitudes are going to come together at one specific point, and the point of concurrency for the altitudes is called the orthocenter. So I'll just write that this is the point of concurrency for the altitudes. I'm not going to make you guys know any more than that. There is some stuff that are special, but that's kind of beyond the scope and sequence of what we're doing in this class. So if you just know that the altitudes all meet up at the orthocenter, that would be good enough. So I'm going to go back up to these pictures and draw in the other altitudes so you can kind of get an approximation of the placement of that orthocenter. If I'm going to here, If I want that to be perpendicular with this side, it looks like probably right around there is where I get my right angle. And I'm just eyeballing this. If you guys could do your best job of eyeballing it, if you have like the corner of a piece of paper or like a little index card or something, that might help you be able to find that right angle. And then this one here, again, both of these should be right angles. They should be perpendicular with that side. Or even you guys could take your paper and kind of rotate it around to where like this is either horizontal or vertical. Seems like those are always easier to see. So for the acute triangle, the orthocenter ends up being here in the middle inside the triangle. If I go to these other triangles, however, from this vertex perpendicular with this side is just right there. And from this vertex perpendicular probably looks like maybe right around there. So the orthocenter for a right triangle ends up being like right on the corner of that right angle or right on that vertex. And then lastly, for the obtuse triangle, this one here is by far the hardest one to get accurate. We'll see how well I do. First thing I'm going to do is I'm going to take that side and extend it. And I'm going to look here. So for this one, it looks like that's probably perpendicular. I can't quite see that vertex. I'll have to move that out of the way. So for this, probably right around there would be perpendicular. But you can see here that I need to take those and I need to extend them so that they continue to be probably someplace right around, I'll make a guess, maybe right around down there. So if I take those line segments and I extend them, so I'm going to extend all these out, and again, this is just kind of an eyeball in it, okay? Not quite exactly, but you can see that someplace down around here would be my orthocenter. If I actually had either graph paper or if I had a compass and I could use that to measure how far these distances are, that should be a lot more accurate. But again, for the sake of this class, as long as you know where the altitudes meet and that that point is called the orthocenter, that will be sufficient for what we're doing.